In the previous module on heat exchanger, we saw how we can determine the mass flow rate of either the hot or the cold fluid flowing inside a tubular heat exchanger. But many times we are interested in determining how long the heat exchanger should be. That's one of the design questions. So in this module, we will look at this figure first that shows a concurrent flow tubular heat exchanger, and it has the temperature profiles along the length of the heat exchanger. And we will consider a thin slice of this heat exchanger and determine the rate of heat transfer in this very thin slice. We will express that as dq from the fluid H, which is our hot fluid, to fluid C, which is our cold fluid. And we can write a simple expression. You may want to refer to the module on overall heat transfer coefficient. So dq equals U times dA times delta T, where delta T is the temperature difference between the hot fluid and the cold fluid. Now that temperature difference delta T between the fluids H and C can also be written as delta T equals TH minus TC. Now for this thin slice, or the small differential ring element as we have seen in the figure, the energy balance for just the hot stream can be written as dq equals minus m dot h times cph, which is the specific heat for the hot fluid, times dth. And for the cold stream C, we can write dq equals m dot c cpc dtc. Note that dTH is a negative quantity because the temperature of the hot stream is decreasing. And that's one of the reasons why we added that negative sign, so that overall we have a positive value for dQ. Now solving for dH and dC, we can rearrange the terms as dTH equals minus dQ over m dot h cph and we have dTc equals dQ divided by m dot c times cpc. Then if we subtract dTc from dTH, we can write dTH minus dTc, or we can write that as d, which is the difference between TH minus TC, equals minus dQ. In parentheses, we have 1 over m dot h cph plus 1 over m dot c times cpc. From the first two equations on this screen, we will substitute the value for dq in the right hand side of this equation. So dq is U TH minus TC, which is from the second equation, times dA. So on the next screen we will substitute this dq. So we have d TH minus TC equals minus U TH minus TC dA, and in parentheses 1 over mH cph plus 1 over m dot c cpc. Now we can take this dTh minus dTc and divide this by the Th minus Tc, which comes from the right hand side of the previous equation, and that equals then minus u dA times, in parentheses, 1 over m dot h Cph plus 1 over m dot c Cpc. So now we are going to integrate, and we use our integral signs, and we will integrate from T inlet to T exit. That's the temperature at the inlet to temperature at the exit, and we have dTh minus Tc divided by Th minus Tc. And for the right hand side, we will integrate minus u and then 1 over m dot h Cph plus 1 over m dot c Cpc, and the integral will be for dA from 0 to the total area of the heat exchanger, A. Now if you look at this left hand side, this looks similar to dx over x, and you know the integral of dx over x is natural log of x. So we can write the left hand side as natural log of Th minus Tc, and it will be integrated from T inlet to T exit. Those are the limits of integral. The same thing here, the integral of dA is like integral of dx, which is x. And so for the right hand side we have minus u 1 over m dot h Cph plus 1 over m dot c Cpc times A. Now the left hand side can be written as natural log of Th exit minus Tc exit, that is when we evaluate it at the upper limit, minus natural log of Th inlet minus Tc inlet. And recall from algebra that natural log of A minus natural log of B equals natural log of A over B. So we will rewrite our left hand side of this equation on the next screen and as a ratio. So we have natural log Th exit minus Tc exit divided by Th inlet minus Tc inlet. So that's for the left hand side written as a ratio. And that of course equals minus u a and in parentheses 1 over m dot h Cph plus 1 over m dot c Cpc. Now recall from the heat exchanger, the inlet side we will call 1 and the exit side 2. So Th inlet minus Tc inlet is delta T1, and Th exit minus Tc exit is delta T2. Those are the temperature differences for inlet and exit. So we have natural log of delta T2 over delta T1 equals minus UA and in parentheses 1 over m dot h Cph plus 1 over m dot c CPC. Now let's look at the right hand side terms. This m dot h CPH comes from the heat balance equation, and recall that m dot h CPH equals Q over TH inlet minus TH exit, and m dot C CPC equals Q over TC exit minus TC inlet. So we can substitute then for m dot h CPH and m dot c CPC the quantities we just determined. So it will be minus UA in parentheses TH inlet minus TH exit, remember they will now go in the numerator, divided by Q plus TC exit minus TC inlet divided by Q. So now we can go ahead and take Q out of the parentheses. So we have minus UA over Q, and inside we have TH inlet minus TC inlet and minus TH exit minus TC exit. We have separated the temperatures for inlet and exit. Note that in the right hand side, TH inlet minus TC inlet is delta T1 and TH exit minus TC exit is delta T2. So now we have natural log of delta T2 over delta T1 equals minus UA over Q, and in parentheses we have delta T1 minus delta T2 for the inlet and the exit conditions. So Q then, by rearranging the terms, Q equals UA delta T2 minus delta T1 divided by natural log of delta T2 over delta T1. Note that the negative sign was absorbed in this equation. So Q equals UA delta T LM, where delta T LM is defined as delta T2 minus delta T1 divided by natural log of delta T2 over delta T1. And we call this delta TLM the log mean temperature difference. So the important equation in design of tubular heat exchangers is Q equals UA delta T log mean, and we have seen how the delta T log mean is obtained.